Oh, then never mind. See,
okay, is your you have the no. Yeah. Make sure your mic is on.
Sir.
Okay. Well, I want to thank Efrain for coming from so far away, just across the atrium here. He's one of the co-organizers, so I'll let you go, please.
Yeah, so in the interest of time, I'm going to actually condense this talk a little bit. So you may be wondering about where this is, this nice picture of these giant crystals, in fact. And it's actually tied to a lot of what some of our previous speakers were talking about, Hanno and John as well. It's about transport and how we actually move mass in some medium, whether it's water or an oxygen, or maybe some other kind of gas or fluid, in order to get nice crystals. Let's see. Does this advance? Okay, hopefully I'll be able to advance these. So yeah, so in fact these large crystals are from the Nika mine in Chihuahua, in Mexico. So actually, it's funny because we have actually, I think, 3 students here originally from Chihuahua. One person from Querétaro, Mexico, and actually, so Chihuahua is a little bit overrepresented here. My mom is from Chihuahua as well. So this mine is located sort of in the center of the state in northern Mexico. And it was discovered because they were looking for some other metals, minerals. And when they drained some of these larger caves, they discovered these giant gypsum calcium sulfide crystals. And so, indeed, this was like a hydrothermal, like a giant hydrothermal reactor, where over thousands of years, these crystals were slowly growing and growing. And I actually met one of the crystallographers from the University of Granada in Spain, who was able to go in here and explore and walk through these crystals. And he tells me that now actually the mining company has backfilled it all with water, and so they're naturally, I think, going to start growing once more again. How do we get this kind of crystal growth in the earth to maybe reproduce it in our own laboratories? Well, it has to do with thermodynamics and chemistry, as Hanno was alerting to earlier. Even in another part of the earth, let's go deeper, at the bottom of the ocean floor, there are these hydrothermal vents where there's chemistry that's sort of out of equilibrium, if you want to think about it that way, right? So even though thermodynamics is going to be very important, kinetics plays a role as well, okay? And how do we get such transport, how do we get such dynamic behavior in your crystal growth process? And it can be done several ways. One that's shown here, for example, in the bottom of the ocean floor, is through gradients in pressure and gradients in temperature, right? And so, indeed, that's how many minerals containing iron and manganese and other metals and metal oxides that otherwise would be insoluble in water are able to precipitate out and mineralize. Originally, you know, this talk is like an hour-long talk, and I was going to talk about chemical vapor transport, and then hydrothermal synthesis, and then something related to hydrothermal called solvothermal synthesis. But in the interest of time, I'm just going to touch on a few principles from chemical vapor transport, and then use those to apply to hydrothermal and solvothermal. How many of you have done CVT growth here? Okay, a lot of people have actually done CVT growth. There are some similarities between the two in the sense that you're doing a closed reaction in a vessel. You're doing a reaction in a closed vessel, right? In CVT, you have to have a quartz tube or maybe Pyrex tube that you put in a furnace with a temperature gradient and so on. Hydrothermal and solvothermal is similar. You're putting it into a closed system, and you're hoping, actually, if you want really big crystals, that you have some kind of temperature gradient in there. So this was the outline of the talk, and I'm just going to go through some of the slides a little bit faster than I normally would. But you'll have all the slides, and I'm here, of course, through the whole week, so we can always chat if you want to know more about it. So CVT is really awesome if you're looking at 2D materials. It's been, I think, one of the most utilized methods to grow large single crystals where the lateral dimensions are in the millimeter range. One of the maybe disadvantages of this method is that you get very thin crystals. Perhaps if you're very much interested in just the 2D physics of it, you can exfoliate and the thickness of the crystal is not such a big deal. For those of us that maybe do like bulk crystal measurements, like neutron scattering or something like that, it can be sort of a limitation, right? And so you have to think about how you can grow as much as possible, maybe thinking about your reaction vessel to maximize thickness. So these are just more examples of crystals. These are transition metal dichalcogenides, and in my lab, we've been doing the thiophosphates, selenophosphates, and also the metal chalcogenides, dichalcogenides like niobium diselenide recently. So one thing about CVT and transport is that indeed you want some kind of horizontal tube that goes into a horizontal furnace, and that you want to have at least 2 zones so that you can put a temperature gradient on it. And then you need to think about the charge zone, which is going to have your starting material, and then your growth zone where your crystals are going to nucleate and then grow. And all I'm going to say a little bit about chemical equilibrium, because this is sort of at the heart of what's going on with these. And that is that we have some kind of reaction going to a product. Our product here is our crystal, right? And the thing about equilibrium is that it's a dynamic process. And so the forward and the back reaction is always happening, in fact. And what you want to do is you want to push equilibrium in one direction. And so that is called the law of mass action, where you have this equilibrium constant, it's just products over reactants. And when John Mitchell was talking about, for example, the equilibrium constant in the induction furnace under high oxygen pressure, you noted that the equilibrium constant was just the oxygen partial pressure, okay, or the fugacity of the oxygen. I'm just going to, again, I'm going to have to go through this one a little fast, but it's all Le Chatelier's principles. So if you haven't heard of this since high school chemistry, to remind you, is that basically it's for every reaction there's an equal and opposite reaction, right? So when you apply some external stressor, such as molar concentration, which is going to affect your chemical potential, temperature, volume, or pressure, the system is going to act in such a way to come back to equilibrium. All right, so if the stressor is to increase pressure, the theme of this workshop, the reaction will move in a way to decrease the partial pressure of species A. Another way to think about it is if you increase temperature, the reaction will move in such a way to absorb heat and decrease the temperature. All right, so that makes a difference if you're looking at a reaction that's going to give you your product, and if that reaction from a enthalpic point of view is going to be endothermic or exothermic. And so, for example, if I had this is from, when I'm teaching Gen Chem to the students in this very lecture room, this is an example that we always use. This is an endothermic reaction. And so we can write it out this way, and we can put heat as almost like it's a reactant here. And so if it's endothermic, right, you can crank up that temperature and you'll get your more product. If it's exothermic, you don't necessarily want to turn up the temperature to get more product, because actually it will do the opposite. It will give you more of your reactant. Okay, so those are some of the considerations, and they actually have a practical implication for your crystal growth. So if you're doing transport between 2 different zones, first, you're going to ask yourself, is this an exothermic or an endothermic reaction? Because that's going to then mean, am I going to have the charge zone at the hottest temperature, or am I going to have the crystal growth zone at the hottest temperature, right? As I said, if it's exothermic, you're going to favor reactant at higher temperatures. So indeed, what you want for an exothermic reaction is you want the growth zone to be the hottest part of your two-zone furnace. And if it's an endothermic reaction, you want the other way around. You want the product side, the charge zone, to be the hotter end of the tube. Okay, so sometimes we get in the habit of just assuming that everything is going to be endothermic, and we just set up the crystal growth so that the charge is at higher temperature and your crystal growth is going to be at a lower temperature. If it was just physical vapor deposition, great. But that's not the case many times, right? If you're doing chemical vapor transport, you have to actually consider how the chemical equilibrium is going to shift. So that's one of the first things you want to think about. In general, sort of a rule of thumb is you want this equilibrium constant to be equal to unity, or 1, and therefore you want the optimal temperature to be the enthalpy over the entropic term, all right? So you can look up the standard enthalpy and standard entropies of your reaction, and then from there you can back out what the crystal growth temperature should be. Now, then, of course, you want a temperature gradient, so you want to play around with maybe -25, +25 for the two different zones in your furnace, and then that will optimize some transport. You don't want to have a huge temperature gradient, because if you do that, then you have transport that's too fast, right? And if it's too fast, you'll get your product, but you'll get a polycrystalline product. So you need to sort of slow it down, have a nice kind of temperature gradient that is very gradual and not so steep, so that you can optimize larger crystal growth. The other limitation on the size of the crystal is going to be just the size of your tube, right? So obviously if you have a 5 millimeter inner diameter, then you're going to get small crystals. If you have something that's 10 millimeters, you'll maximize your chances of getting nice large crystals. So that's sort of the point I wanted to make on chemical transport. So typically, lengthwise, you want something 100 millimeters to 200 millimeters. You want the diameter to be 10 to 20 millimeters. And again, this is the way you're going to find what temperature you're going to do it, okay? So you can do oxides, you can do halides, you can do cachalgenides, you can do other things like black phosphorus perhaps, and other 2D materials this way as well. But it doesn't have to be a layered 2D material. It can be any kind of compound. Let me see, what I wanted to say is, let me go back, whoops, going too fast, is transport agent. So this is an example of zinc sulfide. You want to think about some kind of transport agent that's going to be your part of your reaction, right? Many times we like to choose halides or halogens in the elemental form, like iodine, chlorine, or bromine. I would say, always try to figure out what would be the easiest thing to manipulate in the lab. So with iodine, it's a solid at room temperature. You can pick up a little crystal, weigh it, and then put it into your glass tube or quartz tube and seal it, right? It's not a big problem. Bromine issue, right? You have to pipette some liquid fuming bromine at room temperature. That's tough to do. We've done that before. I've done that before. But you have to cool it in an ice bath or something like that. And so think about what's the easiest thing to do. In many cases, you can look up already what's a known transport agent. There are others besides these. There are some metal chlorides, for example, that you can use as a transport agent. This is a case where just using this rule of thumb, the optimal temperature is about 1,000 Kelvin. And then sorry, this is now in Celsius, but then there are some actual tables where they calculate the partial pressure versus temperature, and you can see where you sort of want equal population of your transport agent in the gas form, so that you can then decompose it back into the zinc sulfide that you're after. So a lot of this, you do want to think about initial temperatures, lengths, and the pressures that you'll get in there, but there will be, of course, some trial and error that's always involved in crystal growth. So, this is a science, but as you know, there's going to always be a little bit of an art to it as well. Let me go through some of these are some of the crystals that we grow in our lab of these antiferromagnetic thiophosphates, selenophosphates. These are Mott insulators, so we're very interested in them, and potentially doping them, charge doping them, and see what happens. Since antiferromagnetic Mott insulators, once they're charge doped, can lead to very interesting behavior, like in cuprates, for example. So let me now get into hydrothermal. So Hanno talked a lot about sort of what you want to think about as far as the container and the temperature and so on. So I'm not going to try to say too much in that respect. You did reference Bell Labs, and I wanted to show the picture from Bell Labs as far as the quartz crystals. Those are the sizes that they could actually get under hydrothermal. So now in hydrothermal, think about it as not using a chemical transport agent, but now using water. And there's going to be indeed something in there like a compound of your metal that's going to transport through the water to get to then decompose and then make a crystal of whatever it is that you're after. Okay. I think there was a question earlier about why water? Like, don't you want to avoid water? I don't know. Yeah, here it was. And, you know, as long as the water itself, just, if we think about it as just helping with transport, you know, it's not going to be detrimental to the system. Many times also when we say something is air sensitive, we put two ideas together. One is oxygen sensitivity and the other one is moisture sensitivity. And you have to really deconvolute the two, because something may be okay with water, but oxygen is actually bad. Or oxygen plus water is bad. Think of iron. Iron with water is okay, but with oxygen, rust, right? And so you have to think about like actually when the two are bad. And so you can take water, you can deoxygenate the water if you're afraid of getting oxides, and you can load your hydrothermal vessel in an air-free container, some kind like an airbag, or maybe you can have a little dedicated glove box, which is what we have in case you're really, really worried about that kind of thing. So there are different ways to deoxygenate your water as well. Okay, so, and then I like this one because I feel like this is just giant crystals. This is from a company in Japan. And these are actually being lifted because the hydrothermal vessels in this case, instead of a bomb room, they have it just underground. So if it, were to explode underground, I guess it would be contained. So this is very interesting history on how hydrothermal was developed to grow artificial crystals of quartz. And you mentioned Lodis, who is one of the most talented crystal growers of all time. And he has a very interesting quote that I think many of us think about here. Everything is made of something. If you don't have the materials technology, you lose the device, you lose the system, the application, right? So you need the actual material to hold in your hand, right? To say, I have a device, I have a quantum material, etc. The other day I read this headline about Google coming up with, the headline was Google discovers 380,000 new compounds. And I was thinking, they don't understand the English language if they think discover means predict, 380,000 compounds. In the end, someone has to make those compounds, right? And so that's why I think this school and this workshop is so important, because we are one of the few that actually dedicate ourselves to thinking about how we make new materials and how we do crystal growth. And I think without Lodis, you wouldn't have had all these wonderful materials to discover new physics, even if it was predicted. All right. For hydrothermal synthesis, how do we define it? Hanno did a great job describing the different versions of hydrothermal, like soft hydrothermal and supercritical hydrothermal. In the end, the commonly accepted definition is just get water above 100 degrees Celsius and above 1 bar of pressure. So even though this is a high pressure theme here, I would say for hydrothermal, it can indeed be high pressure, but it can also be just barely high pressure type of synthesis. And so you can get a lot done under these conditions. Solvothermal is a related term, and when you see that, it just means that we've replaced water with any other non-aqueous solvent, right? And I'll tell you a little bit later about maybe how you want to think about which one you pick, right? Also, we have this mineralizer. It's a solvent. Okay, if it's water, it's fine, but many times it's just not water. It's something else that you put in your water in order to solubilize your reagent or dissolve your reagent. In the lab, I think Stephanie, my student, is working with you on making some zeolites, or at least telling you how she makes some zeolites. Why hydrothermal is important? It's because you're able to access phases like zeolites that have a lot of internal empty space, porous space, that you wouldn't be able to get if you were just doing normal solid state reactions. A lot of the iron-based superconductors I'm about to show you cannot be made through solid state reactions. They can only be made at low temperature hydrothermal conditions, also solvothermal conditions. So many times what may not be on a phase diagram, a thermodynamic phase diagram, because it's looking at really high temperatures, exist under hydrothermal. So you're sort of stepping off some of those well-known phase diagrams. So this is just a historical development of many different kinds of materials that can be made. We mentioned MOFs earlier, these metal organic frameworks. So not just inorganic, but if you want to start bringing in organic as well into your system, you don't want to turn the organic molecule into carbon, right? And so you want to work under hydrothermal thermal conditions to preserve its structure. All right. So this is sort of what some advantages are versus just high temperature, maybe some conventional high pressure techniques. It's low temperature, so you can, it's lower power. Sometimes you can get pure materials. So it's a low energy process, i.e. cheaper. And these are the sort of materials that you can make. A lot of times you want to avoid maybe certain compounds with hydrothermal because they may oxidize under aqueous conditions, all right? Sulfides and selenides seem to be okay. Tellurides, a challenge, okay? So there are some things that you may not be able to do at all. When it comes to quantum materials, some of the very important quantum spin liquids have been made only by hydrothermal methods. For example, Herbert smithite and zinc barlowite, which have copper spin 1/2 on a Kagome lattice. Those are all grown by hydrothermal methods as well. So those you can't access through normal solid state reactions, and you have to go through this route. Hanno touched on viscosity being part of the issue here. So you need mass transport in your hydrothermal conditions. Otherwise, you're not going to grow what you want, because you need that transport, in fact. And the dielectric constant of water actually drops as you go under hydrothermal conditions. I have a table here, and this is the viscosity of water. And you can see as you go under hydrothermal conditions, it drops significantly. So you're able to transport more material so as we can facilitate crystal growth under those conditions. And also the dielectric constant drops as well. So that's kind of interesting if you kind of think about it from a, like dissolves like point of view. Water is very polar, it's one of the classic polar solvents, but many things are not non-polar, but it will become less polar as you go under hydrothermal conditions. So some things may go into solution that you wouldn't anticipate under, at ambient pressure. One of the things you need to think about safety-wise, I would say, is how much you actually fill up the little Teflon cup, right? And so many times when you buy it, it's the 23 milliliter that Hanno referenced. Another standard size is 45 milliliter. You can buy some really big ones too. They get very expensive. But You know, this is filling level, 90%. So you can see at 90%, the pressure shoots up. And of course, you know, we're not talking about the pressures that were presented earlier in this workshop or school. But still, this is, you know, it could either seriously deform your Teflon cup, right, Stephanie? And so, or, you know, it could rupture the actual hydrothermal bomb. And so these are sort of one diagram you want to take a look at if you're thinking about doing a hydrothermal reaction and what conditions you want to be in. As far as getting up to the critical point of water, not a lot of people do that. There's a very simple reason for that. One is Teflon is not going to survive past 210 degrees Celsius, something like that. And so many times we do all these reactions in Teflon, right? Because we want some clean conditions, so the Teflon is fairly clean. And you need some kind of liner. And so during the supercritical growth, there are a few groups in the US that can do this. Joe Colas and, I don't know, Hano, do you do supercritical as well? Hano, yeah. So I think that's about it. I don't know. I feel maybe that not a lot of people do that one.
There's certain things you can make, like there's certain fluorides that we can dissolve at lower temperatures, but it goes very good. You don't even need HF, you just put sodium. Yeah. Works really well. But convincing students to work supercritically is hard.
Right. We had a furnace that could go to supercritical conditions that we inherited from Brian Eichhorn, but it was very leaky, I would put it that way. Yeah. So in any case, sort of the basics are that you need what's called the nutrient, which is your starting reagent. You need to think carefully what you want as your starting reagent. Do I want a metal salt, or do I just want the metal itself? Right? They will give you different compounds in the end, different oxidation states. And so for many of us working on transition metal compounds, which is a lot of us in this room, we want to think about the final oxidation state, d-electron count, and everything like that, right? So that's sort of the consideration. Acidic or basic conditions. For example, on our iron-based superconductors, we almost always work at pH 14, and no less than that. So super basic conditions, because under acidic conditions, you generate a lot of defects in these materials. Why? Because, as Hana was alluding to, we have these pore bay diagrams, these diagrams about pH. They tell us at what concentration we'll have oxidized versions of different elements. And so sulfides and selenides under certain pH can become sulfates or selenites, right? So that's the reason why we were working under certain pH. All right. Thermodynamic principles. JP, I'm supposed to wrap up by noon, or?
Yeah, in a few minutes, and we'll leave time for questions.
All right, cool. Let me go through some of this and just show some of the work that we can do under hydrothermal. I think Hano covered so much of this anyway. I don't know if you mentioned the microwave, but you know, if you want to do fast hydrothermal, you can certainly do that with an all Teflon autoclave in a microwave. All right, one of the interesting systems that you can make under hydrothermal conditions is this iron selenide intercalated by lithium hydroxide. The lithium gets replaced a little bit by iron 2+, so this layer becomes slightly positively charged, and that electron goes into the iron selenide, and it becomes a superconductor up to 43 Kelvin. And what's interesting about this is that if you get enough iron, this layer can become also ferrimagnetic, and so you can make something like a magnetic superconductor. That was one of the reasons we started getting involved in this. The way we made this compound is we made actually an isotopically pure compound. We made all lithium-7, all deuterium, because we do neutron scattering. Lithium-6 is a high neutron absorber, and hydrogen is a horrible incoherent neutron scatterer. Sometimes it's okay. I mean, you can still get coherent scattering from hydrogen, and you can solve crystal structure that way. But deuterium is really nice when it comes to coherent scattering. So we did this chemistry all in D2O. In fact, so you can see the volumes that you work with. And these are sort of an idea of your reagents that you want. For example, we use selenourea, pure iron metal, lithium deuteroxide that we make, and basically the amount of time. So for the hydrothermal practical, for example, you can't go in and get a crystal out the next day. It takes time. And so, you know, this one is 5 days, roughly, sometimes a week. And you can make this lithium iron deuteroxide. It turns out that we just found that D2O is different from H2O in the products that you get. So D2O was much, much better to avoid like iron oxides and other impurities like that. And so that was a very nice sort of fortuitous discovery that we made. One of the things that it still intrigues me about iron selenide as a superconductor is that there have been reports where they put iron selenide on strontium titanate and go up to, and say that they have 100K critical temperature, maybe 65 Kelvin is probably the more settled number. And so what's nice about iron chalcogenides is that you can fill them in with all kinds of ions, molecules, or layers. And so you can do this through hydrothermal methods. If you want to do, I'm going to, again, in the interest of time, just to understand those hydrothermal methods, sometimes it's very difficult to know what's going on. So what we do is we do in situ hydrothermal solvothermal synthesis on the beamline. We go to the advanced photon source, and actually we don't have anything fancy like Dermot O'Hare's setup with sapphire windows or anything like that. We just put in a little capillary tube and quartz capillary, and we backfilled it with helium. We got to 7 bars of pressure, and we start with our reagents, and we're able to watch these diffraction patterns in seconds and see how the hydrothermal reaction proceeds. And so this is the conditions for hydrothermal. You can see the quartz tube sizes, the pressure that we use, and the temperature. And we take, you know, thousands of powder patterns. And this is an example of the pattern as a function of time. So this is from 0 to 1200 minutes. So here we start out with all iron metal, and then we get to our product that we're after here, with some byproducts like lithium carbonates. So there's always some CO2 in water as well, right? It's pretty soluble in water, so you'll generate some carbonate sometimes. So, you know, if you're really worried about things like that, that may interfere with the crystal growth, you can figure out maybe a way to decarbonize or de-CO2 your water. So this was the phase we're after, and then we do Rietveld analysis, we do quantitative analysis, and then my students write some code to do a sequential refinement of the thousands of patterns to get out crystal structure and composition information out of it. And this is just one of the results. This is how the iron goes away, and then the product comes in. And then we're able to see that the iron substitution in the lithium hydroxide layer actually starts out near 20% and then drops out, okay? And so this is one of the reasons maybe sometimes you get irreproducibility in results. Sometimes you get a superconductor, sometimes you don't. And it has to do with the fact that under hydrothermal conditions, the ions are always sort of moving around. And so you have to take that into consideration. And so this is where you would get optimal superconductivity, about 20% charge doping into your iron selenide. And then once you lose it, you'll, you know, basically either kill it off or you come back to 8 Kelvin critical temperature. So you can see that even though hydrothermal, we can think of it as sort of a black box because we put it in this autoclave, stainless steel, right? And we leave it for a while. With some in situ techniques now using X-rays and maybe even neutrons, you can see a lot more. I'll end by saying you can do other things besides water. You can choose other solvents like dimethyl sulfoxide, DMSO, dimethylformamide, DMF we call it, or ethylene glycol. These have much higher boiling points, so you could go up higher if you want to. And these, also have similar polarity to water. What we're trying to do in my lab is use other ones to substitute for water. So we have ethylene diamine, this 1,2-diaminopropane, this diaminocyclohexane. This is, you can make this into like a chiral molecule if you're interested in that kind of, making a non-central symmetric superconductor, for example. And so these actually work very, very well, especially this one. It has properties close to that of water, like its viscosity and its boiling point. So if you want to mimic hydrothermal synthesis, you want to choose things that would be like water. Maybe ethanol, methanol is good. Just be aware that all of these solvents have a hydrogen bonding in them, and so they love water too, so they'll soak up water. And so you always have a little bit of water in your system, unless you work really hard to get rid of the water, like you work in a glove box, you order ultra dry solvent or something like that. Otherwise, you can always count on some water being in there, which isn't a terrible thing, because sometimes water is a little bit like a catalyst in these materials and helps with crystal growth. So in any case, this is an example of an iron sulfide that's structurally similar to the iron selenide superconductors, where we're able to intercalate these different amino groups that we use for solvothermal synthesis. So it's not just the actual solvent, the medium, but it's actually also participating and going into your structure. For us, we want that. In some cases, maybe you don't want that. You don't want the solvent to go into your crystal structure. And if you pull out the solvent, the crystal actually falls apart in many cases. And so you have to, wonder if it's good or bad for you. One of the cool things that we found about this is that sometimes it leads to layer twisting. And so many of us are interested now in twistronics or whatever. And we're able to see this in some of our solvothermal growth. At first, we thought maybe we just had what's called a bicrystal, where two crystals are stuck together. This IPCO cuprate superconductor has that kind of behavior where you have square lattices that sort of twist with respect to one another. We tried the same for our square lattice because it's also tetragonal space group. And we found that, in fact, in many times, even though layered materials, you think of them as just stacking on top of each other, they can actually twist. And that solvent that you grow in can help aid that. So ethylene diamine, for example, led to that. And so we're able to solve some of these structures using something called coincident site superlattices, where crystallographically we're able to describe exactly how you can get a supercell like this from just twisting of your layers based on just the superlattice reflections. All right. You have to solve it in a new space group, but in any case, this is an example of a pattern that we were able to get with these solvothermal syntheses that at first looks very, very daunting, but my student Lahari was able to solve the structures and actually generate all the superlattice reflections with these coincident site superlattice models. I would say in the end, what we want to do, hopefully with these iron selenides, is can we break 42 Kelvin? Can we get something like 65 Kelvin? Obviously, it would be awesome to just get to liquid nitrogen, right? And so our idea is maybe we need to couple the iron selenide with some kind of layer mismatch, some other material that would strain the iron selenide. And so what we're doing is looking again at nature, which grows things hydrothermally. And we found this mineral called toshilinite, magnesium iron hydroxide with iron sulfide. As you can see, this nice golden flakes that are growing here. And what we've done is use that idea to grow these iron selenide heterolayers, where you take that hydroxide layer. These are positively charged, so you can fill them with water, carbonates, all kinds of anions, chlorides. But instead of filling them with those anions, we're going to fill them in with iron selenide anionic layers. And again, we grow these hydrothermally to make these compounds, and we can make the iron aluminum, magnesium aluminum, selenides, and sulfides. And then these are a little bit hard to see, but these are their electron diffraction patterns, and we can generate these compounds and all these superlattice reflections in them that tell us how to solve the structure, at least, and we can index all these superlattice reflections by taking a hexagonally based layer that's able to strain this square lattice layer of the iron selenide. We haven't gotten a superconductor yet, but we've been able to at least learn how to design them chemically and how to solve the crystal structures. They also have some extra lattice reflections that we think may be charge density waves that we haven't been able to solve quite yet, but might be very interesting if they're related to the superconductivity in iron selenide. So I'm going to end that here because I want us to get to lunch and get us back on schedule. Just acknowledge my colleagues here at Maryland and our funding resources and all the students and postdocs in my group that do all this work. And so now I'll hopefully take, I don't know how many minutes you want me to take of questions, but
We'll see.
We'll see, yeah. And we can always chat in the lunchroom as well, so.
Okay, thank you. Any questions?
I have two quick questions. So, what determines the best transport agent for growth? I know you mentioned a little bit about the vapor pressure at a certain temperature.
Yeah. Right. You want to think about the, whether your transport agent will be vapor, first of all, at the temperature that you're going to grow, right? So for many of them, there are gases already at room temperature, so that's not a problem. The other ones will be some solids, like you can get some metal chlorides, for example, like aluminum chloride, let's say. So you want to know that it's going to be vaporized at that temperature. Second, you want to know that basically it's enthalpy and entropy term from that reaction, so that you can then find the temperature that's going to be optimal. Usually it's going to come down to a decision between iodine, bromine, or chlorine. And so you may even just cycle between all three of them and then just see which one gives you like the largest crystals. Sometimes that's what we do. We just experiment to see which one actually gets you the largest crystals. Yeah. And so, so that's the vapor pressure. What's your second question?
The second one is, are impurities an issue for this kind of growth compared to other?
For the CVT or the hydrothermal? CVT itself was a way to refine the compound. In other words, to get pure compounds. So I would say that growth is actually nicer if you want higher purity in your materials. And so, because you leave behind all the impurities in the charge zone, or you should be leaving behind all the impurities in the charge zone. Because of the, this temperature gradient, when I was talking about Le Chatelier's principle, basically you want to push the reaction in one direction. And so that's why in one zone, you should only be getting one compound from that. The hydrothermal is a little bit more complicated because there you actually have a fluid that's moving things around, and so the impurities can be in there. If you can fish out a nice crystal from all the impurity powder, then that's okay, right? But I would say in the second technique, impurities are a much, much bigger issue than CVT. Yeah.
That is if they have different temperature properties. Because you can also mix things if the same crystal is growing with, let's say, different transition metals. Those are impurities in your starting material. They'll end up in a crystal. So if you can separate them with temperature, then that's good. You can be fine.
Yeah. I mean, in some ways, it's a separation technique, the chemical vapor transport. Yeah. So what you start out with may not be what you end up with at the growth zone. Yeah.
Okay. First here, second, third.
So a lot of these techniques allow you to access new phases, but they seem to also require seed crystals a lot. So is it possible to run these techniques without seed crystals at first to get your seeds? And if not, like what techniques do you use to get your seed crystals?
You actually, maybe I was misleading with one of the slides where they had seed crystals. Like that's if you want like those super large, crystals. You don't need a seed crystal at all for any of them actually. If you can get a seed crystal and it works, that's great. But in many cases, no, you don't need a seed crystal. In fact, we never use seed crystals. Hano, do you ever use seed crystals? No. So no, you don't need it actually. Yeah.
I have a question about your iron selenite.
Mm-hmm.
So I wouldn't quite get it, the idea, how can you create physical structures because this is hydrothermal, right? So I guess you put a mixture of the compound, the iron selenite, and the other oxide.
Uh-huh.
How did it end up to be like
Yeah.
how can you control the structure?
Right.
Say the number of layers or orientation?
So there are a couple ways, and I didn't have time to go into it, but it's either if you're going to do bottom-up growth or you're going to do top-down growth in your hydrothermal conditions. Bottom-up, I present it like I throw iron, selenourea, or something like that, right, and I grow crystals. The other way you can actually do it with the system is you can make crystals, really large crystals first, like I wouldn't say it's a seed crystal maybe, but you make like potassium iron selenide, which is congruently melts, so you can grow really large crystals by solid state reaction. Then you throw that in hydrothermal conditions and you convert that from potassium iron selenide to lithium hydroxide iron selenide. And so that will get you like much thicker crystals if that's what you're after. The bottom-up approach typically gets you polycrystalline sample to very small crystals in that case. If you wanted to grow bigger crystals under those conditions, you would have to figure out a very nice way to apply a large temperature gradient, I would say, on your hydrothermal vessel in order to do that. I think your question also alluded to how the stacking, because I was talking about twisting. So in that case, what we did is we either had all ethylene diamine as the solvent for the solvothermal growth, and that did not get us this twisting effect. But if you mix in a little bit of water, so you have some, you can do like 10% water, 15% or more, under those conditions, we start seeing this twisting effect. And so it has to do with your solvent choice, in fact, or how we were able to observe this. We still don't quite understand why that is. It's just something, one of the parameters that we play around with is the actual solvent and its ratio to water. Yeah. Sure.
What might be the reason why compliance or introduce strains to iron selenide
Yeah.
Get this higher.
Right. Yeah, so for me, what I was thinking about was, this report of a single layer of iron selenide on strontium titanate substrate. And so the lattice mismatch between the strontium titanate and the iron selenide, if that affects the electron hole pockets at the Fermi surface, right? Somehow, then perhaps we could do that in a bulk crystal. That's basically what we're trying to do. The easiest way to do that is, of course, to just electron dope. But that, we've done that, and many groups have done that as well. And the highest we can get is 43 Kelvin, no matter what. So our idea was, okay, we not only add charge, but we also strain. And let's see if we can do it by this, what we call mismatch heterostructures, right? We take the square lattice of iron selenide and we take the hexagonal lattice of the hydroxide, and it deforms the square lattice in order for them to actually come together. And so that's our idea. We haven't gotten a superconductor yet because I think we're overcharged doping in this case. So we have to figure out how to kind of scale it back. But structurally, I think we figured out how to do it at least. Yeah.
Yeah, I think in the interest of time, we better stop here, and please, if you have more questions, please ask them. So we're gonna have a bit shorter lunch today, just because I want to make sure we have time for discussion. So 12:15, 45 minutes. Go eat, enjoy. I'll call you back.
All the nasty ones. Yeah. Right.